Okay, everybody seeing the monitor?
Yes, sir.
Alright, cool.
Yes, sir. Hello?
Yes, Franklin.
Oh, hi.
Fine.
Yeah, ma'am.
Everybody seeing the Octave window?
Yes. Yes, sir.
Good.
Yes.
Alright, we can get started now. Few people are yet to come, but yeah, it's not 6:30 yet. I have a minute left, so let me wait a minute. But everybody has seen the other assignment that was posted. Just another MATLAB exercise to get you familiar with some other functions and routines, or we say subroutines. Alright? You know what the word routine means? Not the programming word routine, but the English word routine. What does that mean? Anybody answer me?
Yes, sir.
Say that again?
Yes, I saw the assignment.
So what does the word routine means? What does the word routine mean?
You can use a particular action.
Alright. Or it means a repetitive action, right?
Yeah.
Right. So these we have things called functions and routines in programming. So if something is repeated so often, why not standardize it? And so that's that's what these expressions and such are. Okay. For loops, while loops, and so forth, those are routines, or we call them subroutines because they are part of something else, but they are not functions. Okay. They're sort of operations, but we wouldn't say operation either. It's a routine because it's a routine is a sequence of activities that you repeat over and over and over again. So we call a routine. So I just use it. I'm kind of just shedding light on the word routine, so it helps you to appreciate what the whole programming experience is about. All right.
Okay.
Alright, so let's get into the lecture. Quick review from last week. We've been doing iteration. Sometimes it's called root finding. It's not really root finding. It's just that root finding is one type of iteration. In fact, after we do this particular iteration, unit 4, which is called optimization, is also actually a type of iteration. It will be again some loops that are repeated, or a sequence of activities that are repeated over and over again until you come to a satisfactory answer. But again, it is not normally listed under in engineering analysis. The process of optimization is not normally categorized under the subject iteration. But please appreciate, iteration is more than root finding. Okay? Iteration means to repeat a procedure in which the result of each repetition helps you to improve your next effort of coming to a satisfactory answer. Alright? So we have root finding, we have fixed point finding, and later on I hope to touch on it before I finish tonight. We will also deal with optimization. You're not going to get any other assignments until you have submitted your presentation next week, but your next assignment will be assignment on iteration, and it will cover root finding as well as optimization. Alright. If you want, you can you can let me know that you're hearing me by sending a text sometimes if you want, or just unmute and say something. Remember, if anybody wants to say something, please do so by just unmuting and speaking. Okay? Alright, this is a whiteboard slide. Every now and then I'll come back to this slide. Alright, good. Glad everybody's hearing loud and clear. So every now and then I'll come back to this slide if I have to do some notes. Okay. So quickly, root finding, not root finding, iteration. In this sense, we're dealing with solutions to a function or to a set of functions, a system of functions. And the solutions, usually there are two types of options. There is the root finding, which is a common one, and root finding you'll have several different ways in which you do root finding, and there's a second option called fixed point iteration. Okay, so when you look at this list here, note that this middle one here is distinct from the other 5 that are shown here. The 5 are root finding methods, while to solve a system of equations or to solve an equation. The equation can be any type of equation, can be a linear or non-linear equation. And then this one, the fixed point, is a different approach. Alright? Last week we started looking at the bisection method. Now the bisection method, I don't have to go over this. We'll discuss what iteration is, and so you should appreciate that fixed point and root finding are iteration, and later when we deal with optimization, that's also iteration. So the procedures to do iteration is always to start somewhere. We have to determine, it's like searching for something. We have to say where is the best place to look, or where is the best place to start looking. That's called guessing the solution, the first guess. And after doing the first guess, then each iterative step will refine the solution. Alright? Your guesses have 2 categories. You can have a bounded guess. That means you start off saying your solution, the 9 part. You start off saying your solution is in between 2 values, or it's in a range, and it's a known range. That's called bounding your guess. Sometimes you're not sure that it's in the range, but you can also bound something even if you're not sure. So that's another way you can do a solution or solve a system. For example, you can say, I'm going to try and find an answer, but at first it's like looking on the ground. There is this search and rescue protocol. They call it gridding. Let's say you have an accident. Let's say you had an air accident. Common thing. Aircraft accident. An aircraft blew up in the sky. When it blows up in the sky, the shrapnel is going to fall all over the earth. And then, first of all, the engineers will identify the last location where radar or communication from the aircraft was established, and they'll probably talk to eyewitnesses identify, let's say, the speed of the aircraft at the time, the height of the aircraft, and so forth. And based on all that information, if there was an explosion while in midair, they expect that the aircraft will have pieces flying in several directions. But generally, they would say, okay, we expect that the pieces of the aircraft will fall in this general range, right? And they would limit their search to that range. That's an example of bounding, okay? And they limit the search to the range. And what you're doing, limiting that search now, they normally grid up that section, cut it up into many squares, and you know, and they'd have teams handle different grids or different squares. And a square might not be huge, but it's a very methodical way of ensuring that you search everything. So that's another way we could actually do bounding and iteration at the same time. You look at a region or a bound, like you could say, I'm first going to look if I can find a solution between x equal 1 and x equal 5. And you do your search. Let's say you come up empty, then you can say, okay, I'm going to look between x equal 5 and x equal 9. And you can do it like that. Okay? That's another way of doing bounding. And that type of bounding also allows for several solutions to be found. So that, let's say there are multiple solutions and you don't know how many there are, you could say I'm going to look through the whole system, but I'm going to take ranges small enough that I don't expect more than one solution to be possible within that range. Alright? Are you listening? Everybody understanding what I'm saying?
Yes, sir.
Alright, so that's the importance of bounding. Bounding is always viewed of as being very bounding is normally considered very stable. It's a stable procedure. Unbounding is an unstable scenario, because when you unbound something, you're allowing the procedure to take you wherever it goes. And if you carry it down to the depths of hell, you go down to the depths of hell to find the solution. But bounding says, this is where I'm looking for the answer, and if you thoroughly search that area, you don't find the answer, then you stop. Quite simple. Alright? Anyway, so you have bounded iteration, you have unbounded. We're going to look at the bounded first. We looked at one last week. The bounded case that we considered last week was the bisection method. Alright? One more thing. Oh yeah, we talked about different ways you bound something. How do you choose to bound? You can bound by having a crude understanding of the system. That's generally how you bound something or do an initial guess. You should have a crude understanding of what you're trying to solve, so you could have an idea of about where your answer should be. Alright? It's always unwise to try to find something and you don't know where to start. You have to make a decision on where to start, and where to start should not be a shot in the dark. It must be well informed. Okay? Also, please remember, there's something called the incremental search. Incremental search is not iteration. Okay? Incremental search is a method to find your initial, to find where your iteration should start. Alright, we looked at bisection and we did a little example last week, and there are some others we're going to look at this week. We look at one more bracketing method called false position, which is actually considered probably it's the most robust, quick method of iteration. false position or regular falsy. Then you have other methods. The most common, well-known one is Newton-Raphson, or sometimes it's called Newton's method. And you have secant and Euler's. You see the fixed point form is also an open method. It is not a root finding method, it's a fixed point method. Alright? We talked about the problems already, so I won't go over them again. Just to reiterate, especially you need to understand the system you're solving. Don't let the computer tell you the answer. Let the computer confirm your answer. Remember, that's or let the computer increase the accuracy of your answer. So you should know about where your answer is. The computer is just being used to clarify it, to make it a little more clear, more precise what the answer is. So these are examples of functions and possible behaviors of functions, and these possible behaviors can give you an idea of the issues that may arise when you try and solve especially a nonlinear system. Alright. Okay. Let's say a few things because revision is good. Some other matters regarding iteration. I shouldn't say root finding. Shouldn't have said root finding up here. I should rather say iteration. Another issue regarding iteration. Is when you bound, this is kind of obvious. If you're bounding, you always bound your root where you think your root is, if possible. Remember that some bounding methods, I just said it earlier, some bounding methods do not necessarily mean that you know the root is there, but at least when you bound it, you can say the answer is not there, and you can move to another bound or another range. Okay. Again, I can't sufficiently emphasize the need to make sure that you start at an appropriate location. Very important, very important. Any bounded method, which is the same thing as a closed domain, same thing as bounding. Okay, same thing as bounding, while open domain is unbounded, right? Open domain is unbounded. Some systems, especially in electrical systems, you have complex roots. You must be aware that your solution can give a complex root, and you must understand the meaning of that, what the complex root really means. You must appreciate that you have several different methods. Some methods are quicker, some methods are surer. Now you have to decide what is best. Okay, a surer method is where you have the time, use sure methods. Okay, where you may not have the time, you use a quick method. But appreciating that when you use a quick method, every now and then your system will crash, or you have to the solution procedure may go on for infinity. Alright, so you must, as much as is possible, when possible, use bounded methods. I can't keep stressing that also. When you can, but sometimes you can't bound it, sometimes you have no basis of bounding, and in such cases you use unbounded methods. Alright. Every iterative problem, again, it's an iterative solution. It's just a habit root finding, it says, but it's not necessarily root finding. It's just finding the solution to a linear or nonlinear function or system of equations. There are some when you're writing the computer program now, this slide has to do with the actual computer program. When doing the computer program, there are some things you must keep in mind. You must always put a limit to how long your program should go on before you stop. That means when you say it's getting dark, for example, I'm going to stop searching now. You know, using a real world example of searching. You're outside and you're looking for something. It's getting dark, time to stop. Or may I get tired, time to stop, you know, or this is not working out, time to stop. In the computer, you use a procedure where it's just you actually are decreasing you just establish a certain number. So you could say after 100 iterations you stop, for example. Every iterative method must establish what is okay to say I have reached a solution. That's called a convergence test, and it's wise also at the end of every convergence test or the end of every solution subroutine to be convinced that you have solved it. You actually plug back in your answer, and it is suggested when you're plugging back in your answer, you as a human being with your equations and if necessary a calculator, you actually work it out that way, not necessarily asking the computer to do it for you. Okay, remember, we are the final test, not the computer, or that's how it should be anyway. So we talked about the bisection method. Let me do a slide here, animation. I want to ask everybody to confirm that they're seeing the web page. This is the web page that is referred to on one of the slides. Alright. Everybody see the web page?
Yes, sir. Yes, sir.
Okay, so we're going to do animations for root finding. You realize again the term used here is root finding. It's not really root finding, it's iterating to solve for a function, because you'll see among these animations, I'm clicking on it, you'll see among these animations that fixed point is here. So fixed point literally cannot be a subset of root finding. Okay, you have a root finding iteration different from fixed point iteration. But I'm just saying it again. It's kind of just been a convention or a tradition to call all of it root finding. Okay. All right. So here's a bisection method. It's going to be repeated over and over again. All right. There are two options here. I want you. There's a new page. Is there a new page? Let me check something. This looks like the same old page. Alright, let's go back to what they're talking about. Bisection. Same old page. Alright, here we go. So here is a system. It's actually running through the procedure. I want you to follow along. Just follow along. I'll explain what's going on. So initially, so we have this function. It's written here below. Everybody see where I'm pointing to? I hope you can see my little cursor moving. Alright. So this is the function. It's a cubic function, and what this function is, and so the pink line is the solution to the function. Now this is going to be a bisection method, originally starting Not seeing the pointer? Right now the pointer is under the number 1. It's a very small pointer. Under the number -1. Under x equal -1. You're not seeing it, class?
Don't think I'm seeing it either.
Oh. I need to use a bigger. And
Is it that 4-way pointer thingy?
Yeah.
Oh, it's at the top of the page for me. Yeah, we're seeing it now.
Okay. Alright, so it's right under the -1 right now. Alright, so the -1, or the problem started, the initial guess would have bounded the system at between -1 and 2. Everybody see the range? From -1 to 2. That's the original range. Whenever you're doing a bisection, if you know that you have a solution, one side of the solution must give you the positive value for the function, and the other side of the initial guess, or the bound, must give you the negative value. In this case, the negative is on the left and the positive is on the right, but it could have been the other way. Okay, that's not seeing it. I can't make the cursor any bigger, so I'm wondering how I'm going to make you guys see this. Yeah, my pointer is flashing. Let me... I want to try something else. No, you're seeing it now, Mendes. Alright. Don't worry about the pointer too much. You can listen to what I'm saying. Alright? So, the range in this case, the negative is on the left. Okay? And the positive is on the right. But it could have been the other way. It doesn't matter. It could be either way. And the first thing we do in the bisection is we split the system in 2. So I'm going to reload this page, and it's going to split the system in 2. Let's look at the first. I can't pause it. So the split should be somewhere here. Good. When it had split it in 2, what it did is it determined what the function was at that new split, and then determined should the value, it would have been between -1 and 0.5. Should that be the new range, or should the new range be between 0.5 and 2? And how does it determine that? It just checks which one of the ranges will have the 2 different signs on the limits of the range. Alright, so in this case, let's reload it again. So my cursor should be right at the middle of the range. Reload, come on. Not reloading. Hello. Let me back out and go forward again. There you go again. So right here is the middle. Now the right is the part. And then it keeps doing that. It keeps cutting in 2. The red dot represents the halfway mark each time. Okay? So let me reload again. Got the red dot. Red dot is the halfway. See? Half. 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 And you realize that red dot keeps going around where the actual solution is. Alright? And it iterates until the range goes to almost the same as the solution. Okay? This iteration took 20 steps. So that's a practical, or that's an example of a visualization of the bisection. Let's look at the other case. Now this is an example of failure to know your system. Failure to know your system. So what is the problem here? You have a function, you find two places where it is negative and positive. That means that for one value it is negative, for the other value is positive. And you say to yourself, aha, that means it must be 0 in between. Is that the case here?
No, it's not.
Okay. So because you are not aware of the system, you're not aware of the general behavior of the system that you're solving, you could do iteration and think you find a solution when actually you very much did not find a solution. Alright? That's why your knowledge of the system is very important. And, can't be downplayed that the computer is not, should not be wiser. Alright? The computer is just assisting you, not doing your work for you. Alright? So that's the bisection method. The next method, I'm not going to do the animation, I'm going to go back to the PowerPoint presentation. So let's just talk a little bit more about bisection before I go to the next. Before I go to the next give me a minute, please. One minute. 1 minute back. Alright, so I was saying some of the other issues about bisection. If you don't know your system behavior, generally speaking, it might be challenging finding the initial guess. So you must appreciate why that is very important. Okay? Find that initial guess. Very important, the finding of the initial guess. If it's a continuous function, so you should know math enough to look at the equation and say, you know that the system must be continuous. Continuous means it doesn't have a discontinuity. What's a discontinuity? It means a location where there is no solution. That's what a discontinuous solution is. The case that you just saw, that is with the asymptote and the function approaching the asymptote from two directions. That's called a discontinuous equation, because at this value for x, at that value for x, there is no solution to the function. What clear on what a discontinuous function is, right?
Yes, sir.
Alright. So, but the point is this: if your solution is continuous, or you know it to be continuous, then if you do find a place where one is positive and the other place is negative, then your answer is certainly between the two. This is probably the slowest, one of the slowest methods of iteration, but it's definitely sound. Okay. Again, discontinuous functions can be a problem. Some discontinuous functions can still have a solution. For example, here's an example. Suppose this is where the x was. Let me erase. Let's say the asymptote was actually here. So this is where the x axis is, and this is how the function looks. Then you realize it does have a root, alright? But even though it does have a root, there's a place of discontinuity, and both of them may compete for your attention, and you may bound it improperly and you don't get to the answer. Okay? So again, understanding the behavior of your system is very, very important. Okay, so that you don't allow the computer to tell you foolishness. Now regular falsy, I don't remember which language it is, but English it is translated false position. Regular falsy. Okay. Regular falsy is a little bit more grounded. Let me go to the whiteboard. And let me open another program so I can do a little drawing on it. Guys, give me a moment. A repeated phone call is coming, so let me just check it. Alright. Everybody still there? Yes, so let me imagine. Hold on. So what we're going to do, just for you to appreciate regular falsy or false position, I'm going to open another whiteboard. If I should open a different one. Hold on. Have to use this. Not my best option, but we'll work with it. Everybody seeing this rule sheet? I hope.
Yes.
Alright, so regular falsy does this. Imagine that this is your x-axis, this is your y-axis, and let's say this is your function. Let's change the color. So let's say this is your function. Let's make it more curvy. Alright. Alright, so what regular fuzzy does is, again, we bound the system. So I'm going to actually do the iterative steps here using a highlighter to help us to identify the different locations. Alright, so I'm going to keep pink on the left and blue on the right. So our bones are going to be here and here, first two bones, right? And then these are our first two bones. Sorry. Let's say we start a problem there. So what does regular or false position do? It determines what is the function at the bounds. In this case, we have here a value for the function. What is this value? It's a negative value, a small negative value. And here we have another value for the function. Hold on, what's going on here? So here we have another value for the function. It's a large positive value, right? Everybody see the two values? And what regular fuzzy does is, the first thing it does, it takes those 2 points, and it actually does, to find a new bound, it makes a line. It's like making a line. Does everybody see the yellow line? I may have to change the color if it's too dim. Are you seeing the yellow line?
Yes, sir.
Okay.
Yes.
Good. So when it does that, what it does is, wherever this yellow line crosses, the system is considered. So let's go back to black. So it crosses the system here. That's going to be the new bound. What the bound is, whether it's going to be the left or the right bound, whether or not it's the left or the right bound is not determined. It's going to be determined when we put. So if this is a new location, let me make it in color red, highlight red. So now this is going to be a new bound. No, won't use red, use green. So here's our new range. So the range is either this left piece or this right piece. Which one are you going to use for the range? The right piece or the left piece?
Right.
Good. Use the right, because the left piece is both negatives, while the right piece has one positive and one negative. Alright? Again, you would have to draw another line to the new solution location. Oops, hold on, yellow line. To the new solution location. So the new new solution location now would be right there. And so our range limit is going to be here. Again, we'd only pick the right piece because the left piece would now be two negatives. You see the two negatives, but the right piece would be a negative and a positive. Right? Then we do it again. One more time. Repeat the procedure to the new solution. Again. Right here is where the new bound would be. Right, and again repeat the solution. Right here is where the new bound would be. Again, the right piece is still two negatives, and the left piece would be a negative and a positive. Again, repeat the solution. Okay, and so on. There, and again and again and again. Okay. So repeat the solution. I know this seems redundant, but just want everybody to be clear. And then again, where it crosses, put your solution, and so on. And you realize we kind of getting to the location. Alright, in this case it took a little time to get there, but really what regular falsy does, I'm going to show another case. What regular falsy does to show you that it really is faster than bisection, even though in this example it may seem to be slower. It's actually quite fast. I'm going to let's give a second example. If this was a case, let's say where you had the x-axis, y-axis, and then you had a function that looks, let's say, something like this. Now, what bisection does, let's say this was my bound, so these are my bounds. Say this was one bound, and let's say this was the other bound. Bisection, all bisection tells me is that it's between these two locations. And then I half it. When I half it, bisection says it's going to be on the left or right piece.
On the left.
Good. And I half it again. Bisection will say left or right piece.
On the left again.
It's on the right this time.
On the right.
It's on the right. And I should always let's delete the old rate, the old so it's on the right now, so we're going to delete this one, right? And bisection again, down the middle. Is it going to be on the left or right? On the left. So I delete the right, right? And so on. So all bisection does is that we know that the answer is between the two ranges. But what does regular falsy do? Let's look back at regular falsy. Starting again with the full range. Let's say from there to here. What regular falsy says is based on the value Bedard mute again for me. Based on the value of the two value, based on the value of the two locations, that is based on this value, based on this value and this value, right? What it does is it guess it. False position says we expect the answer to be closer to the one that is closer to 0. So the negative side is closer to 0 than the positive side. Everybody see that? This is closer to 0. Or if I draw a line between the two of them, you realize that it intersects closer to the left side than the right side. So they say, therefore use that value where it intersects as the guess. Alright? And when it finds the solution for that, I'm going to delete the old value. And so now this is the range. Alright, here this is negative and this is positive. So we now make this value the negative, and that value is still the positive. Sorry about that. So this value is the negative right here. So what does the regular falsy do? It says because this negative value is closer to 0 than this positive value, we expect the function to go through 0 closer to this side, and we estimate the closeness based on a straight line. Alright? Actually a straight line there. And you can appreciate that it's what does regular falsy do? It assumes that the function is a straight line between the two bounds. That's all. Alright? And so you can appreciate that if your function was somewhat linear or somewhat straight between the two within your bound, your false position method will get to the answer very quickly, because it's really like what we call linear interpolation. Okay, it's just assuming a straight line between the two bounds. Of course, if it's not a very straight line, it will take a long time to get to the answer, but no longer than what bisection would have taken to get to the answer. Alright? Okay. So I'm not going to go into the coding of bisection. So I won't go into the coding of pause position. All what you can see here, if you look at this equation here, for those who have, everybody has done some interpolation in their undergraduate, and if you look at this equation here, this is really an interpolation equation. Okay?
Oh, sir.
Yeah? Question? Arthur?
No, you weren't saying that everybody has done some form of interpolation in the undergrad.
Oh, you haven't done any interpolation? Well, interpolation means you're in a table, you get some information from a table. Let's say at a certain value, your function, let me delete that, hold on. I'll give you an example of interpolation. So x and y, suppose they say x equals 0.1, x equals 0.5. So let's say they say it is 3.2, and let's say they say it's 9.8, and they say what is y. Therefore, I should do this on the blank slide. Let me do it on the blank slide. So the question, let's use that example again. So here we have case where x is 0.1, 0.5. Let me pick some other values. I don't remember what I had. So they say if that's the relationship, what is y at x equal 5.2? Okay? All we know is that we have a function. We know that at x equals 0.1, the function is 3. Alright? And we know that at x equals 0.5, 2, 3, 4, 5. Let's say this is 0.5. This is 0.1. The function is about, let's say this is where 9.8 is. Everybody understand this graph, right? Yes?
Yes, that's so far.
Alright. So, and then the question is, what is it at, no, sorry, I shouldn't say 5.2, that's a bad case. Let me pick a better value. It has to be a value in between. Remember, so let us say 0.052. No, 0.03. Let's say 0.03. At x equals 0.3 or 0.04. Let's use 0.04. At x equal 0.42, that is, let's say 0.42 is right here. Just giving you an example. What is y supposed to be? Linear interpolation, so you assume it's a straight line between the two values. It's not a very straight line, I know. Hold on. Let's try and clean that up. Do it again. The time we have to do is so there's a sort of straight line. What we say is, to guess what this value is, what we say is the slope of this line. Let's change the color. The slope of the red line. I'm going to draw a red line. Slope of the red line is the same as the slope of the black line. Everybody agree that they're the same slopes, right?
Yes, sir.
and so I'm going to put 0.42 here, and this is y, which is unknown. 9.8 at the top and 3.2 at the bottom. And so we say slope, so we write the two slopes. First slope, that's the slope of the black, is going to be rise over run, 9.8, that's a rise over run. Run is 0.4, or let's write 0.5 minus 0.1. Everybody understand that's a run, right? Equals, and I can do the interpolation from any side. I could say this little black line, or I could say just the red line. I'm going to take, let me take the little black line. Slope of the black line, rise is going to be 9.8 minus what? The little black line at the top, right here. What's the slope of that line?
Minus y.
Minus y. Over. What's the run?
0.5 minus 5.42.
Alright, 0.5 minus 0.42. Good. You realize the only unknown is y. And that's what we mean by it. That's what we do for interpolation. So what false position does is it's assuming there's a straight line between the two bounds, and it's finding when the straight line goes through the value 0. That means it's assuming that, yes, it's trying to determine the value of x, that's the bounds. So let's look at it this way. You want to know when y equals 0, so it could be switched. So I'd have to do another case for you to appreciate that. Nah, I won't do another case. But the point is, it's just assuming that the system is a straight line between. Of course, if it's not a straight line, it will take some time to get the answer. But if it actually is a straight line, then false position will get you to the answer immediately. Alright? Okay, so that's false position. I'm not going to go into the code. You have to do the code yourself if you need to do the code. Alright? But again, you can see here the rise over run. In this case, the rise is at the bottom, the run is at the top. It don't matter, it's just a solution. Alright? The same thing happens. You pick a new value, you find out if it's positive or negative. If it's negative, and you pick the one that allows you to have the two signs on either side of the range. Alright? Okay, let's look at the open domain methods. Open domain methods, we'll first deal with the one that's not root finding, which we call fixed point. Okay? So a fixed point problem. Edward really want me to do the code? Alright, Edward, I will do the code. So let me open Octave. Everybody say Octave. And let me go to, we looked at the bisection method here. Here's our bisection method. Based on our, and I did this in class last time, I wrote this code before, while you guys were with me in class. So what I'm going to do now, I'm going to just change this function to another one called false position. Okay? False P. Let's call it false P, and I'll save it as false P. Now as it is right now, this is not really false position, it is bisection. Alright. Based on, let's go back to this slide here. Good. Iteration. What on this set of cautions or a set of checks, okay, is missing from this iteration procedure? Everybody look at it. If you want to write this down, or you may have it on your computer, go to that slide and tell me what is missing. What is here that is missing from the routine we wrote last week? Anybody? Want me to show you the list again? Okay. Edward say you don't see convergence on it as a check. You don't see a convergence test. Look at the, sure about that? Look at the list again.
Oh, the derivative?
Alright, the derivative is missing. Good. And you recall what is the concern regarding derivative?
It must not approach zero.
Okay, it should not approach it. Good. Anything else missing? Right, remember the final check is not normally done in the code, okay? So that last one, as I said, best if you do it by hand. Or by another routine. Nobody else sees anything else missing? See something missing. Oh, Cargill. I realize you're not muted, but I'm not hearing anything in the background. Is it that you don't have a mic? Oh, alright.
Well, for the convergence test, it doesn't divide by x1, the new value of x, I guess. Is that the difference?
Mm-hmm.
Huh?
No. That's not really. That's not it.
Okay.
Alright. Edward is asking, how do you verify the triviality of an answer? Triviality of an answer would be well, I can't tell you the triviality of an answer. Your every system itself, let me give you an example. Suppose I want to know this is an excellent example. A cannon is going to shoot a ball. Cannon is angled at a certain angle, let's say 30 degrees. The ball has a certain mass, and it's going to shoot the ball initially at a certain speed. And if you're like a mechanical engineer, you might make it more intense, like say a certain amount of power is inputted into the cannon or something like that. talk about efficiency. It's an example of a nonlinear problem. And the question is, when will the cannon be close to the ground, or when will the cannon hit the ground? Okay, and you would have as your function, you want to know what you're trying to find when the elevation or the height of the ball equals 0. 0 meaning elevation. Everybody agree that that's what the mathematical function that you're trying to solve for is, right? Everybody else understand this example so far?
Sir, could the 0 also mean the highest point that it reaches, like a parabola effect, like?
Well, no, that is optimization. Max and min are called optimization. So we're going to get to optimization in the next topic. But suppose I ask, when is the value equal 0? Or when is the height equal 0 for this cannon? Everybody understand the question?
Okay.
You understand the question, Richard?
Sir, now catch it first.
Do I understand? Do I type something and type and then it's like it now come. Okay, y equals 0 being the height, right? So you want to know when it hits the ground, because we're saying at the ground y equals 0. Alright, Edward? Alright, now Dwight, you want to ask a question? Okay. The man can just unmute and say something if you want. Now, if you solve that system, you're going to actually get a trivial solution. One of the possible solutions is going to be, and suppose the question is, at what time is the system going to be, is the ball going to be, or hit the ground, or at what time will the ball be at a height of 0, which is when the ball hit the ground? You know, one of the solution is going to be, the ball will be at the height of the ground at time equals 0. Trivial solution. Why is that an answer? It is true because you fired the ball from the ground. So the ball was on the ground at time equals 0. So it's an example of a trivial. But the point is, I can't give you a general rule for trivial solution. That is why you have to check and you must understand your system. Okay? Oh, I get some feedback from the rest of the class, so I know so I'm not listening.
Yes, sir.
Alright, good. So that's a trivial solution. Again, I said trivial solutions are not necessarily confirmed by the code. It is what you do after the code runs it to confirm that you are the person who is thinking, not the code. Alright? And you can tell the code say a foolishness if I tell you. Alright, cool. But there's still something missing from the algorithm here. So I'm going to tell everybody in few minutes, few seconds, give you 10 seconds. Tell me what is missing.
For this one, X-mid, the way we plan X-mid is different.
Well, yeah, it's different, but it's...
But this one is half in it, for first position, it's different.
Right. No, but this is the bisection still, but the point is still, we do have an error test. Right? The error test is here. Okay, the absolute value of the range. Okay, that's fine. Min minus max is still correct. It's min minus max of the previous iteration, but it's still correct. Okay, because remember, min here is either the mid or the max. Either this is the, look at it this way, Orlando, it's the same one, because either the max is mid or either the min is mid. Okay, so it would still be the same convergence test. Alright. Anyway, what is missing is that we did not, the very first one on the list, we did not establish the upper limit in the number of iterations. What do we mean by that? Before you start it, might be something like just saying n equal, just by saying we start at n equals 0, and in the code we just say n equal or n plus plus. Anybody knows what that means? It's in your assignment. Anybody know what
That's 1 to n.
Huh?
N plus 1.
N equals n plus 1. Alright. Okay. So what are we doing is I don't know, but that it should be good in electrical engineering. You should have some good coding experience. Others, so this is saying every time I go through the loop, when I reach right here, if n is at 0, change n to 1. Okay, now when I go back up the loop, I go to this location, n is 1 still, I go through the loop, when I get to here, n is 2, and so on, and I keep going. So what I want to do now is I want to say while the error is what it is, and I'll put an and I'll say, for example, n is less than 100. What does that mean? So as long as I'm far away from my answer and I have not been in the code for too long, you're going to continue going through the iterative steps. Alright? So what I'm going to do, we're going to still use the false position method, and I'll use the bisection method. I'm going to, let me out the bisection one also. We're going to see how long bisection takes to get to the answer compared to how long false position takes to get to the answer. Alright? So let's open the bisection code. Everybody follow? So I'm going to do 2 codes. Save the bisection. I won't change it again, and save the false position. So everybody say 2 of them, right? And both of them are going to be, and oh yeah, and this line now, to update this line in the bisection also. Alright. Okay, so let's make the changes to false position now. We still, in false position, you still have the limits, but now to find out where your mid is, you're going to use not just the middle, but you'll use interpolation for your mid. Okay, so what I want everybody to do is looking at, let's go to the function. Here we go. Looking at this expression, I want you to tell me how you would, I want you to all type, everybody type what would replace this line. That is all you're replacing. Okay, it's all you're replacing, that line. So instead of saying it's a halfway mark, you're going to say something else. So everybody type what you think it should be. You hear me, right?
Yes, sir. We're thinking.
You're thinking. It's all there now. I'm not gonna make it look so hard. Repeat. I'm asking you the difference between the bisection and the false position methods is only when you're finding a new limit. Bisection say split the thing right down the middle. That's what bisection say. But false position say use interpolation to guess where you think the function might be 0, and that would be where your new limit would be placed. So I'm asking you, so this is the line, this line that is highlighted is the line where you identify what the new limit should be. Okay? Now all I'm asking you to do is to change that line to now be what it should be for the false position case. What I'm going to do, I'm going to go back to the PowerPoint. I want you to write down the equation. It's procedure 3. Write the equation down by hand. Everybody should write it down. Yes, Dwight, that is, it's just that line, just that one line is between the false position and the bisection method, nothing else. Everybody please write it down. Tell me when I can go ahead and go back to this spreadsheet. And when I'm actually putting in the answer for the spreadsheet, I'm just going to copy it from your chat window. Okay, everybody, write it down, write it down, write it down. Okay, Brandis, give me an answer. Anyway, let's go back to the spreadsheet, to the I want you to carefully look at what I have and carefully look. You have something like that. So if I copy what you have, Brandis, and plug it in right there, I'm good to go. No. So fix it up then, Brandis. Let's try to type something too.
Sir, I feel like I'm going to say it instead of type it.
Orlando, you're kind of close. I want you to be very careful with every character. Landa, you're close. Still
Is
not.
it underscore? Is it underscore?
Sir, no, F max, X max will come first. When of X min, should it be the X max?
Is it underscore, sir, for the X-Men?
No.
X-Men.
Just look at my program. Just use back the same variable names exactly as it is there. So I can just copy from your message window and just copy into it. That's what I'm asking you. Yeah, Bedad said leave out the underscore, because if you look on my code, there's no underscore there.
Oh, does the underscore represent the minimum value X min?
Yeah, but no, what I'm saying is in my code I don't use the underscore symbol in the code. I know you're looking at the what you had on the PowerPoint, but I'm saying no, in the code, what would you put in the code? Alright, so Jayan, alright, you're getting there, almost there but not quite. Almost there but not quite. Channel, I think the F min should be F max. D first, the first. To go back to the slide, insert. Alright, I'll go back to the slide. You're writing it down, insert?
Yeah, writing it down now.
Alright, write it down. Please remember, the characters used in the code don't have to be. What I have on the slides is more representative. In the code now you have to be precise, very consistent. Why everybody a buffer? Okay. So let me Devon, let's see what you say. You have a smartphone, Devon? If you have a smartphone, you might be able to put it, well, not for today, but for the next session. Okay, go back to the code now. Okay, I'm going back to the code. I'm looking at everybody's solutions and seeing what everybody say. But that is a little more close. Remember I said I just want one line to replace what is there. Wow. You see when one person does something wrong, everybody is doing but the same wrong thing. Anyway, let's look at it. Everybody have everybody is like trying their utmost. Okay, good. Alright. let me take a few people have there's a little consistency, you know. Some people that throw a whole heap of brackets because they wonder if the bracket are the problem. Fix up your own Brandies. You have a little bracket problem there with your F max in the denominator, you see it? It's not the bracket. Brackets is not the issue. Everybody missing something. Alright, I'm going to take Sean Roy's. He seems closest. All being that him have so much brackets which are unnecessary, but we'll work with his. Still not the answer, but we'll work with it. Okay. Like Brandis want to try something again before me post the answer. You want to try something again, Brandis? Insert, you want to try
Alright,
something?
sir, we can get a hint.
You want a hint? You don't want me to get the answer. That's nice.
No, we don't give me an answer. Just give me a hint, sir.
Well, let me look. Probably it's okay. Let me check something. X mid equals F min. Hold on. I think it might be there now. Let me see. S means F min X max minus F min F max minus. Yeah. So you guys are there now. That's correct. Insert. Well, what kind of man is that? Emoticon with your own. Anyway, that's correct. So you generally are all. You're kind of correct now. Don't worry about it. You're fine now. So yeah, Shana Roy's, Brandy's, most people are okay. What I'm saying, I'm just going to copy over what you have and put it right here. It is okay. But as I was saying, you really didn't need to put these two brackets. Alright. And that's the same exact thing. So now we have, so this is now the first position. Insert to say your last. You still not get it? So here, so this is the first position case. Yeah, I understand, Edward. You're down. I'm not sure why. It probably is your internet connection. Everybody else is hearing me okay, right? Okay. Yeah, check your internet connection, Edward. So you realize the difference between the bisection and false position is simply where we determine the new limit to be. Alright, so I'm going to run both of them now for the same case to see how quickly they converge. Alright, so let's save that. Let's go to the command window. Remember, we were doing the case for the square root of 2, and we're saying we expect the square root of 2 to be between 0 and 4. I think we said that, right? So I can just say bisection. By the way, you realize that my commands from last week were saved. I don't even have to go back. I don't have to type over even what I typed last week. Quite nice, isn't that? Okay, I'm going to use that error and then I'll run it. Bisection, line 15, column 6. go there. Bisection, line 15, column 6. Possibly the n++ not working. I doubt that. But let me write n equal n+1. Just in case something is going on that I don't know about. And I'll put it also at the false position. And I'll check that later. Alright. That's incrementing. And let's go back to the command window. Nope, same thing. Nothing is wrong with the plus plus. What's going on here? Line 15, column 6. Line 15, column 6. I don't see what the problem is. Unless there's something having to do with n. Is n a problem? See that I shouldn't be using n. Is n a special? Nope, n is not a special thing. Let me check something else.
Do you have to redefine the function false p or no?
I did define it already. Here it is.
Oh, define it already. Okay.
But it's a bisection and I'm running. Not the false position one. Bisection when I'm running, I'm not sure why it's not running, so I'm just doing some quick checks. So the n equals 0 runs. MATLAB style short circuit operation performed for the operator. Oh, my AND. So I must check my AND operation. See if I didn't do my AND properly. Let's check AND, help AND. See if I made a mistake here. Not sure what's going on. Let's just do a check. 1 and 1 gives me 1. That's fine. 1 and 0 gives me 0, and 1 or 0 gives me 1. So the AND operator is fine. Let's check something else. If n, while that, and I want to know, go and help me and look, you know.
Should you put a semicolon after the words? At the end of that?
No, I know. Sure that. But they're saying something with the AND.
Mr. the code, sir. Use 2 ampersand.
Alright, I'll do that. Not sure why that should work, but let's see if it works. Yep, it worked. What does the 2 ampersand mean?
Something dealing in C++, it mean the same and but is when you have the boolean. So when you test with true or false.
Oh, with so this is the term short circuit evaluation. Have no clue what that means. Alright, thank you.
Yes, sir.
Alright, so we're going to put the 2 ANDs in both cases. So I'll do it also for false position. Put a second and now I can put back my save them both. Alright, so let's do it again. Command window. So here's what I'm going to do now. I want to find the number of, so there's another thing we can do in MATLAB. This is going to return two values. It will return the value of x and it will return n. What is n, by the way? Anybody can tell me what n will be?
And I count a number of iterations.
Right. And I'll do it for this one also. Now the default is, if I run the code like this and I just say x, it will only give me the first one. It won't give me the second one. Alright? That's the first value. But if I say x, I don't even have to call it x, I can call it t and z, just to make you don't think you have to use back the same values. Alright? If I use t and z, it just calls t the first case and z the second case. What is z in this case?
Number of iterations.
Okay, everybody clear on that? Hello?
Number of iterations.
Yeah, man. Good. So now I'm going to do false position. False position is exactly the same code. But I just write false p. Okay? In this case, took a long time to get there. Interesting. Hold on. Quite odd. You know what's happening with this false position here? Anybody can tell me what happened? Can anybody see what's happened here?
It's about 100 iterations.
Alright, I set it to 100, so what happened? It came out of the solution routine before reaching to the solution. Now, understand what I say?
Yes, sir.
Based on how the shape of the function is, it turns out that false position actually makes the system take a longer time to get to the answer. Understand?
Yep, sir.
Go back to the editor.
So what you would have to do now is, for example, I could even have a third thing that says if n equal 100, two equal signs, then I say statement is going to be a text. Okay, and then I could say else if else, not else if, else statement. No, I shouldn't say solution found. I should say too many iterations, solution not found. Alright, and then, or I could state instead solution found. You could even do a dialog box. Let's do a check if I can do a dialog. Just checking. One moment. Now I remember. Help. This is very interesting. Everybody look at this. I'm going to do message box, okay? So what I'll do is I won't even use statement. I will just use a message box. MSGBOX. And repeat it again. By the way, this should be up here. My apologies. Message box. Oops. MSGBOX. And then I say endif. End function. Alright, so that should do it. I'm going to put back the n++ here, so we are okay with understanding its role. I'll do the same thing here. Save. Save. to run it again, everybody? Let's run them again. So let's do bisection first. See what I just did? Ooh, fancy, yeah. And let's do the other one, false position. Do the same thing. Alright. So you'll be surprised how some of these software programs that you have, some of them might be just written in MATLAB. You'll be surprised at what you can do with MATLAB. Okay?
Or instead of using message box, I think you can use the menu option as well.
Menu option, yeah. The message box is explicitly just to send a message. Menu gives you some buttons usually for you to select from, right?
Yeah, I think mainly used when you expect one input.
Alright, so everybody is clear. So you realize the differences are pretty subtle between bisection and false position. Alright, I want to get to a fixed point though. So what I think everybody might have appreciated that exercise. Did you? Good. Alright, so back to the domain. So fixed point says, or do I say much right off the code? The code is going to be saved. You want me to post the code on the website? I'll post the code on the website. In fact, I'll post it while I'm talking to you, so I don't forget to do it. Yeah, so the fixed point method here now is a little different. Get rid of this. It's a little different. Is when you have a problem and you solve it for itself, in a sense. So I'm going to give you a simple example. If you want, we can use back the same case that we have where we're finding the square root of 2, and you're going to recognize how much we need to appreciate our understanding of a problem to be able to solve it properly. Alright? So let's go back to a whiteboard case. Can we do the same problem? X equals the square root of 2. Let's see. Alright, we're going to do x equals the square root of 2. And I'm going to ask you to bear with me now. Alright? When doing x equals the square root of 2, bisection says, let's go to the whiteboard. What we're going to do, is I'm going to write out the expression x equal the square root of 2. Of course, that is the solution is there, the square root of 2, but you know, to solve for it, I know this may seem odd to you, but to actually get the actual value, remember that the computer only does multiplication, division, addition, and subtraction. Alright, so what is done, if you look at this last slide, what we want to do is we want to express this same statement in a functional way of g of x equal x. We want to put it in that form. I'm going to, it still might not make sense to you, but I'm just going to do it, and then when I do it, I think you'll appreciate it. So what you have here, if I go back to the last slide, sorry, go back to the last slide. No, not that last slide. Alright, so what we have here are some different options for g of x. I'm going to show you that these options actually are still the same. Alright, the first option says g of x is 2 over x. G of x is 2 over x. So let's see if that is true. If g of x is 2 over x, then it will be 2 over x equal x. That means 2 equal x squared. That means x equals square root of 2. But the point is this form is called a fixed point form. It means on one side is always just the variable, and the other side is a function of the variable. Alright, fixed point form. So this is one option, one fixed point option form. Alright, let's look at another option. There's another option. G of x is minus x minus 1 over x minus 2. Let's see if that's still true. So go back to the whiteboard. So what we say is g of x is minus x minus, what was it? X minus 2 over x minus 1. Minus 2 over x minus 1. We're saying that's g of x equals x. This is a little trick here, but we'll go through the procedure. Let me erase everything else on the slide. So we're going to solve for, see if we can do some work on the system. So I can multiply it through, it will become x squared minus x equal minus x minus 2. That's when I just take this and multiply it up here. Everybody should see that. And combining both sides, it would be x squared minus x plus x plus x minus 2, pardon me, equals 0. Everybody see that? And then the x is cancelled there, so it becomes x squared minus 2 equals 0, or x squared equals 2, or x equals square root of 2. This is a fixed point form. X is a function of x. Alright? Hope everybody following. Let's do another case. Another case. Sorry, shouldn't be the last slide there. Let's go back here. Let's look at this case. that case, x squared plus x minus 2. So let's write it up here. X squared minus x minus 2. That's g of x equal x. Again, solving for it, I would have
X squared plus X.
oh, it's plus, sorry. Plus, so you realize the plus is on both sides, those cancel, it becomes x squared minus 2 equals 0, x equals square root of 2. Everybody see? All of these are fixed point forms. What all of these are saying is you're trying to determine, let's erase everything on this slide. So what you're really doing is you have a function, two functions. One function is y equals x. Hold on. Sorry. Let's do it on the other. You have two functions. One function is this is the y-axis, this is the x-axis, and what we did is we drew two functions. One, let's do the first case. One is g of x equal x, and the other one is h of g. Let's call it h of x equal, for the first case, 2 over x. Alright, so note, g of x equal x is going to be this function, same thing as y equals x, and this other one, everybody should know how that function looks. That function looks something like this. See if I can draw it. I hate drawing on the board, just like drawing on a whiteboard. Something like that. Everybody see the two functions? That is when I write when is g of x equal h of x. It's really what I just asked. Where do these two lines intersect? This line is h of x, and this line is g of x. Alright? And I want to know when the two of them intersect. Okay? And g of x is x, h of x is 2 over x. And so when I write that, these two intersect where x equal the square root of 2. So really all we're trying to do is just find out where two lines meet on the y equal x line. It's called the fixed point method. Okay? Yes, clear. So we are recording. Alright. The fixed point is usually one of the more challenging things to grasp. So you're going to bear with me as we go through this. Alright? Let's go back to the... So what this shows you is that you could have several functions for which you're trying to find. All of them intersect the y equal x line at the same value, because all of them start with the same x equals square root of 2, and we just manipulate it and come up with different forms, so that on one side of the equation is just x and the other side of the equation is a function of x. Okay? So how do we do it? This is sort of like saying, if I plug in my value for x, will I get back my x? That's all we're doing. So what we do is we start with the initial guess. Remember, these are called open methods. It's only one value you start with. In this case, the value you start with is 1.3 in all cases. Alright? Then what we would do is, let's use the first case where x equal 2 over x. What do? We say we plug 1.3 into that, so it's going to be x equal 2 over 1.3. What do you get? Somebody pull out a calculator. What do you get? This will be called x0. x0 equal 1.3.
1.54.
1.54. So you're going to say x1 is 1.54. Okay? Then you're going to plug that in. X equal 2 over 1.54. What do you get? Turns out you're going to get 1.3, by the way.
1.3.
Yeah, so it will be x2 equals 1.3. Of course, you realize this is just going to be oscillating, right? Between two values. What iteration does, what fixed point does do though, is that it says sometimes when you plug in your value here, your answer is closer to the true answer. So another case where we see that happening is for the case of, let me use this one. This one is very good. X plus 2 over x plus 1. Let us confirm first of all that that is a correct fixed point form. So what it said is, let me erase all the okay, good. Evan is back with us. So let's look at the other case. So the other case said g of x equals x plus 2 over x plus 1. Let's confirm that that is actually true for our scenario. So it would be x plus 2 equal x squared plus x. Alright. Oops, sorry about that. X squared plus x. And you see the x's on two sides cancel, so we are left with 2 is equal to x squared. Therefore, x equals square root of 2. Everybody agree with that, right? Therefore, so this is a proper fixed point form. Now, what we're going to do is we're going to say x equal x plus 2 over x plus 1. We're going to plug in our first value, which is 1 point. In fact, I won't even use 1.3. Let's use 2. Okay, let's use 2. Let x0 equal 2, and then we're going to iterate x1, x2, x3.
1.33.
Good. So x equal 2 plus 2 over 2 plus 3 equal, this is x1, right? 1.333. 2 plus 1, sorry. 2 plus 3. Alright? Everybody agree with this? 4 over 3. So it's 1.33 or 4 over 3. Let's do it again. Plugging it into this equation again. X equal 4/3 plus 2 over 4/3 plus 1. What do you get? This is, by the way, this is 6/3. This is 3/3. This is 10/3 over 7/3. 10 over 7, right? What's that?
1.43.
1.43. We could do it again. X equal 10/7 plus 2 is 14/7 over 10/7 plus 7/7, and the answer is going to be 24 over 17. And what's that?
1.41.
1.41. And I'll stop there. So you realize the converging. The point is, when I plug in 1.43, I get 1.41. If I plug in 1.41, what do I get? Alright, let me just use the same fractions. So it would be 24/17 plus 34/17 over 24/17 plus 17/17 equal 58 41. Now what's that equal to? Hey Lou? 1.41. So the point is, when we plug in 1.41, we now still get back 1.41. Right. Okay. What just happened there, I don't know. Go back to slide. So just to show you, you have different options here. This last one is the one that we just did. Okay, this one is the one that we did at first. What you can see is that some of them converge, some of them don't converge. Look at this one. This one is, we call it diverging from the answer. Even though we started very close to the answer, you realize the answer after 6 iterations, it is 149 gazillion. I don't know what that number is. Okay, after 2 iterations, this is within 1%. This one really doesn't get to the answer. It oscillates. This one gets to a incorrect answer. Realize it's not true. Okay, I guess it's true. I mean, negative is also a square root, but if it's a positive one, this won't give you the positive one, it will only give you the negative one. Alright? And this one doesn't give you the answer either. So what we realize is that there isn't a one, when you're doing fixed point, there isn't a one function that you work with. You're going to have to pick the best function. Alright? And the best function is based on what we call what's the best convergence criteria. In fact, by the way, this whole procedure, what you're learning here is actually how the roots of square root and cube root and all them something there back in olden days and from the time of the Babylonians. This is how they would find the square root of numbers. Remember, all they really could do was do addition, and that's all we still do. addition, multiplication, division, and subtraction. Every single mathematical operation is still just those four things. So they found a way to do it. How did they do it? Using iteration. Okay? And they came up with a pretty complex function. Which gets you to the square root of a number within 2 or 3 steps. Okay? So for example, if the number was the number was 2, or you look at this case here, the number was 2, this expression would read x, oops, sorry about that, let's go back, this expression would read x equal half x plus 2 over 2. Or x equal x over 2 plus a half. Is this correct? I want to make sure I'm not messing up here. So this becomes x over 2 equal well, minus. Let me make a little check here. Don't want to be mixing it up. Oh, there's an error here. Sorry about this. There should be an X here. So I have to fix this slide. There should be an X here. So fix that. Alright, there should be an X here. Alright. Everybody following? Anyway, when you do it, that's when the X is put there, which you'll see that that is the that is a fixed point form. So let me fix that. So it would be, let's say we're doing the case of 2, it would be 2 over x. So this would be 2 over x. This would be that 2 over x. So let me see. X equal 2 over x. Oh, this should be 1 over x, pardon me. And then this should be 1 over x. So this becomes x squared equal 2. Yeah, that's correct. Or any other number for that case, if I write it out. Let's go back to the whiteboard just to be clear. So the Babylonian method. Finding the square root. All we say is that x is equal to half of x plus the number, let's call it n, over x. And let's solve for it. We get x equal x over 2 plus n over x. So this becomes x over 2 equal n over x. Solve for x becomes x squared. Oh, n over 2x, pardon me. Oh. So this becomes x squared equal n, and therefore x equal square root of n. Alright? But the point is this is what you'd be doing the operation on. Only subtractions, divisions, multiplications, additions. And when you do this operation, eventually the x will turn out to be the square root of n. Alright? Note from the Babylonian method, this is the Babylonian, this is what we got as our best option. Realize it is within 10 significant digits after 3 iterations, and actually after 1 iteration it's pretty satisfactory. It's within 1% after 1 iteration. Okay, this one is within 1% after about 3 iterations. So you see the difference, right? Okay, so there's something called theory of convergence, and I'm not going to bore you with it. I just want you to appreciate that some cases, this is what we had here, some cases converge, like this converges, even though it converges to the negative value. This is converging to the positive value. This diverges. This doesn't really converge or diverge, it just doesn't go to the answer. And this isn't really converging or diverging either, it's just not going to the answer. Okay, but this we call divergence because it's going far from the answer. Alright, so there's a theory of convergence. It's actually pretty straightforward. All it's saying is that if the solution exists, and we know that the function is continuous, so let's say you know the range where the solution must exist, and you know that the function is continuous. Not only is the function continuous, but the slope must be continuous. What do we mean by the slope being continuous? The value of the function doesn't go to infinity. That's what we mean by it's not continuous. That is, it is continuous. The value of the function doesn't go to infinity. And the slope, it just means the function never becomes a vertical line. That's what we mean by the slope being continuous also. So the function never goes straight up or down, and the function never goes to infinity. As long as you know that the function is like that, which in most cases you may know that, then it says if the slope of the function is less than 1 in that range, it will converge. If it is greater than 1, it will never converge. The magnitude, that is. I'm going to actually show you examples just so you appreciate it. It's pretty easy for you to practically see the difference. Alright, let's go back to the whiteboard. Let's clear it. So all we have here, remember, let me do it on the other one. On this one, so what we have is the axes, one axis, the other axis. This is the y equal x line. This is the y equal x line. What's the slope of this line, by the way? Can everybody tell me what's the slope of that line? the derivative of that line. That is, what is dy dx?
1.
1. Good. So convergence theory tells us, this is all it's saying, if the slope, let me show you, let's go back to if this magnitude of the slope is less than 1 in the range, then it will converge. If it's greater than 1 in the range, it will not converge. So I'll just give you some examples. So if this slope is 1, less than 1 would look like a shallower or a steeper plot.
Shallow.
Alright. So anything that crosses like this, all of the red lines, would be solvable, or it will converge until all the blue lines would not converge. These blue lines are steeper than 1. Alright? All the red lines are shallower than 1. I'm going to do some animations for you to appreciate it. Alright? So the red lines and the blue lines represent the function. You know, like, when I say the function, just imagine, for example, that this was a function, this is the function, you know, it started like that and it went like that and it continued. The point is, when it crossed the y equal x line, it had this slope. Let me just re-emphasize what I'm saying. So this is the function. The point is, when it crossed y equal x line, it had that slope. Okay, I think that's a little, try and make it a little neater. Sorry. So we're imagining this to be g of x. So here g of x, it crosses it with that slope, but if it ever crosses at a steeper slope than the y equal x line, then it's going to be a case where it will never converge. Alright, let's look at some animations that show the point, that demonstrate the point. Alright, fixed point iteration. First case, everybody see that this one, the slope is it greater or less? Why don't I answer me?
Less.
Right, less, so it should converge, right? And what we see that it's converging, it's finding the point. So in this case, what happened is that our original value was like this looked like about 0.1. Okay, so it plugged in 0.1 and solved for the value of x, and it got something like 0.4. So it plugged in 0.4. When it's plugged in 0.4, it got about 0.9. Everybody seeing where the arrow is pointing? My arrow?
Yes, sir.
Alright, and it plugged in 0.9, and when it plugged in 0.9, it got about 1.3. When it plugged in 1.3, it got about 1.5. When it plugged in 1.5, it got about 1.67, and so forth. I'm going to reload so you can see it again. So it started at, I said about 0.1. Let's see if that's where it started. Right, 0.1. And it got 0.4. When you plugged in 0.4, it got about 0.9 something, 0.9, 1.3, plug in 0.3, 1.6, or 1.6, 1.78, somewhere there. and so forth till it got to the answer, which is about 2. Alright? Let's look at another case. Now we're going to start on the other side. Plugged in 4, it gets the answer of 2 point something, 2.9 about. Plugged in 2.9, gets the answer of about 2.1, and it's going toward the same value of 2. Alright? Everybody following? In both of these cases, the slope is shallower than a slope of 1. Now, let's see if we can see some other cases here. Here, this is also shallower than 1. It's a negative slope. Remember, it's a magnitude, you know. Okay, so it is still shallower than 1, and you see it converges. Alright, albeit a negative slope, it still converges. Alright, everybody hearing me?
Yeah.
Alright, let's look at the other case. So now you're going to see this is the case where it is steeper, and let's see what happens. Plug in this value very close to the answer, and what do we see happening? Good, divergence. Alright. Now, it's not that you necessarily have to calculate the slope. I just want everybody to be clear on this. It's not like you have to do some differentiating and so forth. If all you have is have a knowledge of the value of the function at one location within your range, and you have the value at another location within the range, you can approximate the slope. And when you approximate the slope, you get a value greater than 1, then you can say, it's going to converge. So you can run your fixed point iteration procedure. Alright? You don't actually have to do the differentiation. For example, in this case, I could have just said, calculate the function at x equal 1, and I would have gotten this value. And then I say, calculate the function at x equal 4. I would have gotten another value. And then I would say, okay, what's the slope between those two lines? When I calculate the slope, I realize that the value is greater than 1. And so when I do that, I say, okay, this won't converge, so I won't really use this fixed point function. Alright? This one is going to go on the other side. Note again, it's going to diverge. Now guess what? This is a very important case. I want everybody to give me your assessment of what's happening here.
Is it going to convert at 0?
Yeah, it's going to converge at 0. So what is happening here? You're right, it's converging at 0. So what's the implication?
You're going to get that trivial, not trivial, it's going to be wrong here.
Yeah, it's a trivial solution. It's not wrong, you know. Look at the function. Everybody look at the function. It's written there. The function is x equal x squared over 4 plus x over 2. Obviously, x equals x something plus x something. The trivial solution is x equals 0.
Yeah.
You don't have to do some iterative procedure to find that. Everybody see that?
Yeah, that 0 is a solution.
Yeah. And you understand why it's called a trivial solution, right?
Because it's a solution, but it's not the right solution.
It's not the right solution, it's an obvious solution. Trivial means obvious and not helpful. It's not giving me any information that I need. That's why we call it trivial. Okay? But guess what? If you run your iterative procedure, you get a solution, and you may think you get your answer. And the worst thing is, you're not going to get exactly 0, you know, remember it's going to go to an error. So you'll get 1 point something times 10 to the minus 3. You'll get some number you think you actually got an answer. So you have to be careful. Alright? But if you actually did the convergence test around where you expect your answer to be, then you would have found out that, you know, I shouldn't use this. So what's happening is the system fails the convergence test around the true solution, but it actually meets the convergence test around the trivial solution. Alright? Everybody heard of this a while ago? Okay, the Newton-Raphson function. I know it's now 9 o'clock. I think we should call it a night. So I will call it a night. Newton-Raphson might give you some homework or some reading ahead. Should I try to? No, it's too late. 9 o'clock. Everybody brain has shut down now. So let's pick this up next week. Optimization should be easier, or it shouldn't be so hard because it's still iteration and it's actually going to draw back on the some of these very same procedures. Alright, while iteration is trying to solve for a certain function value, optimization tries to solve for the max and the mins. Alright, for those who have done operations research, you have done some optimization there, but it's only for linear systems. I think that you would have learned optimization. Am I correct? Alright. So the optimization that is being taught here is optimization for nonlinear systems. Just as you have iteration is a way to solve a nonlinear system, similarly the optimization routines that we're going to discuss will be for nonlinear. Of course, every solution that applies to nonlinear systems apply to linear also, but it doesn't go the other way around. Alright. Everybody please make note of your assignment, your little MATLAB assignment. I know some people already are versed in MATLAB, and if you are, still do the assignment, and there are those who are not, and so you have that assignment to help you to get yourself a little bit more tuned to MATLAB. You will need to know all these little skills toward the end of your project, where you're going to have to do your code, and you'll have to use a lot of loops and so forth. Please note, there is a part of the MATLAB code or the assignment that tells you to code a little procedure, and it says in as few lines and characters as possible. You're going to do this. Therefore, Richard is not hearing. Let me say that again. You have an assignment, a MATLAB assignment. It's just for you to get used to coding for those who don't have the MATLAB coding, for those who don't have the experience. Or some of you actually did do some everybody probably touched on programming, or most of you, but you learned programming in probably in a context that didn't connect with engineering. So I'm hoping to kind of reconnect you to at least some of those concepts and bring it home in a practical sense. Alright? You'll see in the assignment some little coding challenges. Just saying I need you to do, the question will say I need something to be done, and it will say in as few characters as possible or in and as few lines as possible. The essence is simply this. I want you guys to compete. I want you guys to push each other and say, I want to do this. I can do it in 2 lines, in 20 characters. You could do the same thing in 1,000 lines, but the more lines you use, the more prone you are to error. That's why part of coding is to minimize the amount of lines that you use. I hope everybody understands what I'm saying. When you minimize your lines and minimize your characters, then you improve your chance of, if there's an error, you can identify the bug more quickly because you have a simple system. Alright? This assignment is going to be due before your presentation, I believe. I have another assignment coming up. It's going to be assignment based on iteration and optimization and all those things, but I'm not going to have your minds wrap around that until you finish your first presentation. Okay? Any other questions? Or any questions?
Sir, do we have a final exam for this question?
I am troubled about that one. I've been toying with whether or not I want to give you guys one. Of course, you're going to all say no, you don't want one. But yes, I did say I wanted to give you a little concept test, not some calculation. I used to, when I did do tests before, it was more some calculations. But then I thought to myself, you're using the computer. I don't want a test to ask you to use the computer. So I'd rather have a test that is assessing how you think. Alright? That is all it would be. Just a test to assess how you think through a problem from a numerical analysis perspective. Everybody understand?
Not necessarily looking forward to.
Pardon me?
Not necessarily looking forward to that.
No, nobody ever looks forward to a sit-down test. Everybody likes projects and assignments.
I think the project is very consuming as for doing an exam onto that.
Oh yes, I quite agree. The project is going to be consuming. That's why I say it wouldn't be some intense exam, but I may downgrade the value of it. But I still think it's important that you that you demonstrate individually your, you know, thought processes, how you think through framing a problem and so forth. Okay.
That's where the assignments come in, yes.
Yeah, but still you're encouraged to work together in assignments. So the test now is to confirm that your working together has actually assisted you individually in understanding and handling a question independently if necessary. Alright? Don't be troubled, don't be troubled. I was looking back at the breakdown on our system. Tests, you have assignments worth, what I'm going to do, I'm going to make assignments worth 30%, and I'll make the test worth 10%. Alright, your first project will be worth 20%, and your exam is going to be, your exam, which is really the second part of your project, I'll make that worth 40%. Okay, your first exam or your first project is 20, the second one is 40, and your assignment is 30, and the only individual part, which is going to be the test, will be 10%. Alright. Hello?
Agreed.
Okay.
So,
Here, sir. Yeah.
Alright, so that's it. No, what is called exam is going to be your final project, the one where you have to write your own analysis software. That's your exam, okay, and present on it and all that stuff. That's your final exam. Although it's going to be group work, everybody will be graded individually in the presentation. Alright. All this before December.
November, sir. November ends.
No. We're going to go in December. We're going to go till the week before. The week before Christmas. Let me confirm the date. So we have 1, 2, 3 year final. So we have 4 more weeks. 1, 2, 3. Yeah, you have 4 more weeks. Last one would be, it would probably be the 15th of December. Okay. The reduced schedule, which was fewer classes, was to put more burden on you to do self-learning, but still accomplish the instruction in the given period. The fewer classes was to also manage the traveling to UTech, right? But given that we are working on the online method, and it's working out well, thanks be to God, we're going through another session without a hitch, pretty much. And everybody have them little hitches. Even face to face you have hitches, right? So we can say, yeah, it's going well. So because of that, we're exploiting it, and we meet every week. Alright. Again, please remember the Tuesday sessions, 6 o'clock, 9 o'clock. I'm just here. I'm not running a class. I'm just kind of kicking back. Anybody come, anybody have any question, you just holler. I might not even be sitting in front of the computer. I'll just turn up my mic. Might be chilling with my family or whatever. So I'll mute my side, but if I hear anybody holler out, then I will show up and we can chat. You understand? 3 people showed up at the last one. I want you to exploit it more. Okay? And for those, and yeah, that's it. Also, anybody in a really dire circumstances, you can meet me only on Monday evenings. If you're a working person outside of UTech. Otherwise,
what time is there?
that's before 5. And it's not necessarily long because it's like I have about probably 5 different people or different groups of persons I have to meet between 1 and 5 o'clock on Mondays. It's kind of that's like my office and consultancy times. Alright? But for persons who are in the UTech area, you can also check me on Thursday mornings between 11 and 1. But please set an appointment, or please contact me at that time, because it's not like I sit down and twiddle my thumbs because I don't have nothing to do. I'm at UTech, but folks are, demands and responsibilities are always there. But if anybody makes a request, send me a WhatsApp, that's fine. Cargill, if you check, the ENE is up and the grade is up, but we're still having some struggle with the ENG5011. That's the not operations research, the project management and the risk and reliability courses. It's kind of out of my hands, but it's not really out of my hands. I have to be working with somebody in the systems on the system side, the ISAS thing, because there's some bug. We're trying to get that sorted out. So just bear with me, all right? Even on the weekend, I'm trying to communicate with the person to get it addressed, all right? So that's it, everybody. Have a good night. Thank you for your time. God bless you all. And while God bless you all, which He always does, make sure you bless Him. And take care. Not that He needs you to bless Him. He's quite fine. Just for your own sake. The recording should be up by tomorrow evening, alright?